Hi there, in this video we're going to continue covering rules of exponents, but we're going to move to radicals and their properties. So first of all, a radical is something like the square root of a equals b, and what this means is that b squared equals a. So a perfect square, when you take the square root of, you get that number. So the square root of 4, for example, is 2 because 2 squared is 4. And so similar when you have different power radicals, so the square root of n of a, or sorry, the nth root of a equals b, then means that b to the n equals a. And so here are some of the properties of radicals, which are similar to the properties of with exponents. So if you have the radicals multiplying inside a radical, then you can split them up. And if you divide inside a radical, you can do the radical of each one and separate them. The radical of another radical, you can multiply the index. This is what's called the index of the radical. So m and n can be multiplied. And here are some examples to show you what that is. And the nth root of a to the n is a if n is odd, and the nth root of a to the n is the absolute value of a if n is even. And here are some examples as well. So let's try using those properties to simplify some problems. So let's simplify, and we'll start with the fourth root of, say, 32 a to the fourth b to the 7. So the idea here is we want to be able to find perfect fours. So since the index of a radical is a 4, we want to make the exponents match. So 32, let's start with 32. So if there are some shortcuts that you can use, right? I know that 32 doesn't have a fourth root, but 16 does, and 16 is a factor of 32. So I can say 16 times 2 is 32, and 16 has a fourth root. A to the fourth, that's already to the fourth power, so that's great. And the b to the 7th, so we're going to want to rewrite this. So b to the 7th is b to the 4th times b cubed. So we want to be able to match the exponents. So I'm going to write b to the 7th as b to the 4th times b cubed. And then notice, right, when you multiply the same basis, you add the exponents. So 4 plus 3 is 7. So it's the same thing, but this allows us to take the fourth root. So the fourth root of 16 is 2. The fourth root of a to the fourth is a, as stated in the property above, right? The nth root of a to the n is a. And in this case, because it is a even, you could even say is the absolute value of a. And the fourth root of b to the fourth then is going to be the absolute value of b, because it's even. So I'm going to have 2 times the absolute value of a, the absolute value of b, and the stuff that is not circled up here, that means it doesn't have a fourth root, so I can't take it out of the radical, so I'm going to be left with 2b cubed. So you can simplify this as 2 absolute value of ab and the fourth root of 2b cubed. And this will be your final answer. If we are told a and b are positive, are greater than 0, so then I don't need the absolute value. If things are already positive, the absolute value of a positive number is positive. So if a and b are greater than 0, then my answer will just be 2ab, the fourth root of 2b cubed, which I believe in your homework in web assign you'll be told assume that a and b or any variables are positive, so you won't need to worry about the absolute value. But I wanted to illustrate this property 4 and property 5. Since we had an even root here, the fourth root, then we want to make sure that we say is the absolute value, unless we know that they're positive. So oftentimes you'll be told that they're positive. So let's try another example. B, the, oh, I wanted to show you a different way of doing it. So the other way that you could do this problem is, right, if I started with the fourth root of 32, a to the fourth, b to the seventh. This might be a longer way, but just to get the practice, maybe you might want to do it the longer way first and then work your way to the first way that I did it. So this would be, so when you break up 32, 32 is 2 times 16, and then 16 is 2 times 8, and so forth. And so when you write it, we want to say this is 2 times 2 times 2 times 2 times 2. There are 5, 1, 2, 3, 4, 5 2's. And then same thing with a to the fourth, and then b to the seventh. So this is why I'm saying this is the long way of doing it. So it's 1, 2, 3, 4, 5, 6, 7. I need one more. So when you do it the long way is just once you get enough practice, you'll start seeing, oh, I can just do this, and then you go to the short way. Because the index is 4, so that means we want to group things by 4s. So 4, a group of 4 here of 2's, so that means that can come out of the radical as a single 2. And then there are 4 a's, so that means 1a can come out, and then 4 b's, 1, 2, 3, 4 b's, so 1b can come out. So if you can match to what the power of the radical is, or the index, then those can come out. Now the things that didn't get grouped in a group of 4 are the 2 right there and these 3 b's, so that will be b to the third. So my final answer is 2ab, the fourth root of 2b cubed. So the powers left inside the radical should always be less than the index of the radical. So if I had something here like a 5 or a 6, I know I have to keep going because that will be larger than 4. If I have a 1, a 2, or a 3, that's okay because that means I can't make a group of 4. Alright, so let's try. So that's the long way. Ideally, you want to work your way to being able to do it the short way. So let's try now the square root. So now the index, when there's nothing there, that means the index is 2. So it's a square root. Let's say 16x cubed, y to the 6, and z. And we want to simplify this. So same thing, we want to look for perfect squares of 16. 16 is a perfect square, is 4 times 4. So it does have a square root. So this is going to become, I'm going to leave it at 16 because that's already a perfect square. X cubed, the 3 does not match up with the 2 here, right? The index there is a 2. So I'm going to split up x cubed as x squared times x. Right, this is an x to the 1, so 2 plus 1 is 3, so that's okay. Y to the 6, how many y squares can I get out of there? 2, 4, 6. And then the z doesn't match any powers, so now I can take the square root of everything that is a perfect square. So 16 is a perfect square, x squared is a perfect square, y square, y square, y square. So when this come out, the square root of 16 is 4, the square root of x squared is x, the square root of y squared is y, and there are 3 y squares. So then that's what comes out. And the thing inside the radical will be just the xz. So my final answer will be 4x y to the third, right? Multiply same base, you add the exponent, so there's a 1, there's a 1, there's a 1 there. 1 plus 1 plus 1 is 3. The square root of xz. And this is sort of like an intermediate way of doing it. There are so many ways that you can do these radicals. A faster way would be if you have 16x cubed y to the 6 and z, you can just write this as 16x squared x, sorry, and then y to the 6. 6 is divisible by 2, so I can just leave it. And so when things come out of the radical, will be the 16 comes out as a 4 because the square root of 16 is 4. The square root of x squared is x. And now for the square root of y to the 6, I would essentially take the power here of the y and divide it by the index. So 6 divided by 2 is 3. So a y cubed comes out. And then you're left with the square root of just xe. And you get the same answer. And so that's a slightly faster way of doing it, which is really helpful when you have really high powers. So if I wanted you to, for example, simplify the cube root of something like, let's say 27a to the 12b to the 35, right? We don't want to be writing all of those. So I can say, well, I know 27 is 3 times 9, which is 3 times 3. So 27 is already a perfect cube. Now, because the index is 3, I want the exponent to be divisible by 3. So 12 is already divisible by 3. 12 divided by 3 is 4. So an a to the fourth is going to come out. 35 is not divisible by 3. But I can write 35 with something that is divisible by 3. So we're going to say, what's the closest thing to 35 that is divisible by 3? So I'm going to write this as 27, a to the 12, b to the 33, because 33 is divisible by 3 times b squared. And so now I'm going to have the cube root of 27 is 3. The cube root of a to the 12 is a to the 12 divided by 3, which is 4. And the cube root of b to the 33 will be b to the what power? And this is where you're going to take the power, 33 divided by the index, which is 3, so I'm going to get 11. So it's going to be b to the 11. And the only thing that didn't come out is the b squared. So you're going to have the cube root of b squared. And that's a much, much faster way of simplifying, especially when you have those high exponents. What about simplify, let's say the square root, going back to square roots, 27a squared plus 63a cubed. How do we simplify that? And let me take you back to the properties of radicals. So notice that in the properties of radicals, there's nothing here that says if you're adding two values, if nothing says the square root of the nth root of a plus b or a minus b. There's nothing in there that says that you can split those up. So be careful. We don't want to split up over a plus. We can only split up things when they're being multiplied. So in this case, we got to think about factoring. So what do 27a squared and 63a cubed have in common? That is a perfect square. So the index here, my radical, has an index of 2, which means we're looking for perfect squares. Looking for perfect squares. So that's 27. 27 is not a perfect square, but does it have a perfect square factor? Yes, 9 is a perfect square factor. So let's see, and 9 goes into 63 as well. So 9 is a common factor of 27 and 63, so we can take that out. And then a square goes into a cube, so we can take a square out, and that's a perfect square as well. So what are we left with? So from 9 to make a 27, I need a 3. In the a square, I factor it out. Plus 9 times what gives me 63, and that'll be 7. In a square, to get an a cube, I need another a. And so now I can split this up using the first property of radicals, the product property, the very first one. If you have the product of two things, you can split them up. So in this case, I am going to say This is then using that property of radicals, the square root of 9a squared times the square root of 3 plus 7a. And these are perfect squares, so the square root of 9 is 3, the square root of a squared is a, and I'm going to be left with the square root of 3 plus 7a. There's nothing that tells me that I can split up a radical over addition or subtraction, so let's not do that. So this will be our final answer. In here, let me just say I'm assuming that a is positive, greater than 0. And then I don't have to worry about the absolute value. If you're not given that a variable is positive, then you have to say the square root of a squared will be the absolute value of a. And one more example of these, and then we'll move on to scientific notation. So simplify, let's try x squared square root of 16x plus the square root of x to the fifth. Again, there's no property that tells me that I can combine radicals over addition, so we have to, these are not like terms, so I have to simplify this radical. So I'm going to have x squared times, the only thing that's a perfect square here is the 16, the square root of 16 is 4. So I'm going to have 4 times the square root of x plus x to the fifth can be written as x to the fourth times x, right? The index here, remember the index is 2, so 4 is a multiple of 2. So I'm going to say this is then the square root of x to the fourth is x squared, and you're left with the square root of x. So always write the number, the coefficient in front. So I'm going to have 4x squared, the square root of x, plus x squared, the square root of x. Are these like terms? Yes, they both have x squares in them. And this has an invisible 1 there, so I can combine them. So this is going to be 5x squared times the square root of x. When we combine them, I only combine the coefficients, right? The x squares are what makes them like terms, the x squared, square root of x. So I'm going to combine just the coefficient, the 4 and the 1. 4 plus 1 is 5, so I have 5 of those. And that's simplifying radicals. I'm going to make a third video of rational exponents in scientific notation.